Hello and welcome back to our plasma survey course. This is lecture 24. We're getting really close to the end of the course. Let me start by reminding you where we were at the end of lecture 23, and that's where we're going to pick up from. What we were doing was to look at waves in a warm plasma, considering both ions and electrons to be free to move. Then we did not actually derive the dispersion relation. I just wrote it, and that really looks like a good homework problem. But I will at least give you the result, and then we'll do a little bit more work on it today. Okay, let me just write it again. We have, this is the Z component of the dielectric tensor. And that's what we have to use to look at longitudinal waves in warm plasma. Okay, then we have two terms that are very similar, one for the electrons and one for the ions. They look exactly the same, except for the subscript E for the electrons and I for the ions. We have in the numerator the plasma frequency for the corresponding species. Remember, omega plasma ions is much smaller than omega plasma electrons because of the mass dependence in the denominator, or square root of the mass. If you look at the omega plasma and not at its square, and we have the spatial dispersion that comes from the presence of k square in the denominator. The ion and electron pressure in general can be different, and so can be the adiabatic index, depending on how ions and electrons move, and so can the density if our plasma is not actually quasi-neutral. And if ions are not singly charged, then there is going to be a factor that depends on the charge of the ions. We've already looked at the first solution, the one where we neglect omega plasma ions. Now let's look for the other one. The second solution will be found, well, again, we could just solve the second order equation for omega squared. It's not that hard, but it gets pretty messy, as you may find out in your homework. However, we can write an approximate solution by assuming that omega, or if you prefer omega squared, is much less than omega pi squared. That is we assume that omega is small. Come on now. There. Okay. Let's see what happens. Actually, there is a bit of a shortcut that you can take, but it may be worth to do a little bit of work here. Okay. What I'm going to do is just multiply the denominators and get an equation where omega appears in the numerators, and that I'm going to figure out what the main terms to keep are, and I'm not going to do the whole thing. I'm just going to sketch how this will go. All right. So we have omega square minus k square pe gamma e divided by me and e times similar term in the other denominator, k square p ion gamma ion divided by m ion n ion. Then I have minus omega pe that multiplies omega square minus k square p ion gamma ion. Sorry, this is square. Omega p square divided by m ion n ion minus omega p ion square, similar term that multiplies omega square minus k square pe gamma e divided by me and e, and all of this is equal to 0. Okay, I'm going to do just one more step. By expanding the first term, the product, here I get omega to the fourth minus, you see that I have omega squared that multiplies the two terms that both have k square p and so on. So I can collect those terms, k squared times p e gamma e over me and e plus p ion gamma ion over m ion and ion. This all multiplies omega square. And then I have the product k to the fourth p ion gamma ion p electron gamma electron divided by the product of the masses me and e ion and ion blah blah. And then the other terms I'm going to leave alone. Let's see, maybe easier to write it on the next line. Omega pe times omega square minus k square p ion gamma ion divided by m ion n ion times omega square minus k square p electron. Oops, sorry. What happened here? I didn't, well, sorry. I didn't keep up with myself by writing terms, and I lost some pieces. Okay, omega square minus k square pe gamma e divided by m and e and e, and all of this is equal to 0. Okay, then what you have to do here, which I'm not going to do in detail, is evaluate the size of each term and only keep the bigger one. And it's obvious that one thing that you're going to throw away is omega to the 4th. Well, I hope it's obvious. And by evaluating the size of terms, you should be able to figure out what to keep. And the way you do this is by taking the ratio of various terms and figuring out which one is big and which one is small. And you're going to be able to do that for at least some terms just by using the assumption that omega is small. For other terms, you have to make some additional assumptions that hopefully will be physically based. Now, possibly simpler way, if you can keep track of what you're doing, even if it's simpler, arguably a faster way to proceed is the following. Start from the original dispersion relation and figure out what you can neglect and what you need to keep. And this is maybe a little less intuitive unless you're you're at least a little familiar with the way this is done. The estimation of terms. And not trick, but the key is that there will be a second solution if in the original dispersion relation, which I'm showing up here again, the second and third term are of the same order, and notice that they're both going to be much larger than 1. And I encourage you to check the statement if you're not convinced. Well, then, looking up here, we see that if you assume that the ion and the electron pressure are roughly the same order and the densities are of the same order, of course, the mass of the ions is much larger than the mass of the electrons. That tells me that the term in the denominator of the second term is bigger than the one in the first term, so I can neglect omega squared with respect to the electron term, and I'm going to keep it with respect to the ion term. Otherwise, I'm not going to have any omega in my equation. In summary, what's left, what we have to keep for the approximate dispersion relation is the following: minus omega plasma electrons square divided by minus k square Pe gamma E divided by Me and E minus omega Pi square divided by omega square minus k square Pi gamma I divided by Mi and I, and all of this must be equal to 0. Okay, and this is now fairly straightforward to solve. You multiply by the two denominators, actually multiply by the first term and by the inverse of the first term, and that leaves you with the following. Let's see if I can get it straight. Okay, I'm going to take this to the right-hand side. K square Pi gamma I over Mi and I. Far so good. And then careful with the signs. So since I'm taking this to the right-hand side, I change the sign one more time, and I get omega Pi square over omega Pe square, and that multiplies the k square Pe gamma E over Me and E. All right, it's not too bad. And that's equal to, let's see, I can collect a k square. And I can simplify the expressions for the plasma frequencies, can cancel out the common terms. That gives me gamma I Pi over Ni plus gamma E Pe over Ne, all multiplying 1 over mass of the ions. The mass of the electrons in the second term cancels out through the ratio of the plasma frequencies. I think I got everything. Yes, okay. And that leaves me that omega square is equal to k square times gamma ion T ion if I replace, oops, no, that's not the way I want to write it. Pressure over density with temperature. the way we did before, plus gamma electrons, T electrons, everything divided by just the mass of the ions. Hope I didn't lose any pieces, but the result looks reasonable. And I can, well, let me square this first, because this is our final result. I can define, where is it? Sound speed as C sound square equal to gamma ion T ion plus gamma electron T electron divided by mass of the ions. Where here I can make again the assumption this is equal to 1. And in general, whether that's equal to 1 or not, this is going to be of the order of the temperature of my system. That could be the temperature of the electrons if I assume the temperatures are similar or the electrons are warmer than the ions. Divided by the mass of the ions. In fact, there is a couple of things that I've assumed or used that I need to be more specific about. And in fact, there is a couple of things that those couple of things come from kinetic theories, so we cannot derive them in detail. One piece is that these waves are strongly damped unless the electrons are much warmer than the ions. And that's the real reason why these are typically written with the electron temperature. If the electron temperature is not much larger than the ion temperature, and these waves don't really matter because they die away very quickly. That's what strongly damped means. The other piece of information is that in this case, electrons have the time to stream through the wave in one oscillation. They're moving much faster than the ions. And by virtue of that, again, in a way that we can only be hand wavy about, they tend to be isothermal. Let me write this in a different way as a proper sentence. Electron motion tends to be isothermal for these waves. That means that gamma E is equal to 1. So that's where that comes from. Last but not least, these waves are typically called ion acoustic or ion sound waves. Ion acoustic, or ion sound waves. Okay, and that's all we can all we're going to say about waves in a warm plasma. The more complete treatment of waves in a hot plasma is given by a kinetic treatment, which we're not actually going to do. So this is going to be a good stopping point. And next, we're going to switch to the topic of magnetohydrodynamics, and we can also look at waves in an MHD fluid treatment. But in order to do that, we are first going to refresh our memories on the MHD model, which we kind of already saw when we talked about fluid models. I'm actually going to go briefly through that following our textbook so that we're aligned with our textbook. Very well, then let's get started. I'm not sure what happened. And for this course, at least, we're going to only talk about ideal MHD or magnetohydrodynamics. And this is a big field of research. There are textbooks that just deal with ideal magnetohydrodynamics, and probably need a couple of courses to go over them. But we'll just touch on some things, starting from the general set of equations that make up magnetohydrodynamics. And I'm going to start saying MHD to save some time now. The first is definition for mass density. I should mention MHD is single fluid model. Okay. Letters got mixed at random. Now it's a fluid model. That means that I need a mass density, which is defined as color rho sub m in the book notation, where m stands obviously for mass, sum over the species of the mass density of the species. Where the mass density of the species is the mass of the species times the number density of the species. Basically, this is mass density of the ions, because electrons have a much smaller mass. And the fluid velocity is the mass weighted average of the velocities of the species I'm going to use the symbols that our textbook is using, but I'm not going to resist very long. I don't like capital U for the velocity. Anyway, in that notation, the average mass weighted average velocity is 1 over the mass density times the sum over S of rho, sum over the species of density of the species times the velocity of the species, where this is the fluid velocity, that is the average velocity of all the particles. And again, this is approximately the ion velocity. These mass density and fluid velocity are the two quantities that enter the continuity equation, which we can now write. Which is actually the more properly maybe called the mass continuity equation. Most often when people say continuity equation, they mean, that's what I mean, the mass continuity equation. Anyway, that equation is simply the partial derivative, of the mass density with respect to time plus divergence of mass density times fluid velocity is equal to 0. And this can be obtained from similar equations for each species. And just again by summing over the species. And as already come through our discussion of fluid equations earlier, this is basically, well, it's identical actually to the mass continuity equation in fluids and fluid dynamics. And notice that the definition of the velocity needs to be the one we're using up there, not just the average of the velocity of the species. And that if we use that average, you will not get this equation, which points to the fact that the mass weighted average is the physically meaningful average to use. Now, for the momentum equation, that requires a little bit more work and also different spelling. It's been a challenging day. And the way you do it is by summing over the species. We have seen this for in our discussion of fluid models, but I point this out again quickly. Sum over species of derivative with respect to time of mass density of the species times velocity, average velocity of the species, plus the sum over the species of the divergence of mass times UU, and let me point out that this is the divergence of a tensor, second order tensor, then that will give me a vector. But U is two-dimensional quantity in the sense that it's a 3x3 matrix or three-dimensional space. And taking the divergence brings the number of dimensions down by 1, it turns into a vector. Okay. And this is equal to the charge density times the electric field plus J cross B minus here the divergence of the sum over the species of the pressure tensor divergence, of course, could go inside, but since it's a linear operator, but this is the form we want because we want to express everything in terms of quantities that are common to the two fluids. Them are not common, are the appropriately weighted combination of the two fluids. And then there is the collisional term, which is obviously 0. I'm write it as our textbook does with delta C. That's a variation due to collisions of the momentum. I would not have used P for the momentum since we're using it for pressure already. But what can we do? The rate of change of momentum due to collisions. I'll just call this collisional term. The point is that if electrons, let's say, give momentum to the ions through collisions, the ions receive momentum from the electrons. When I do the sum of the two, I get 0, as I should, so that the total momentum is conserved. The definition of current density and charge density are obvious. Now, there is little distinction that needs to be done. I'm actually going to skip the terms, skip the steps, but it is common practice to use pressure that that is defined in the frame of reference that moves with the fluid. And this pressure tensor, the one in this expression, which comes from the integral of VV in dV, and the pressure tensor that moves, I'm sorry, in the frame of reference, pressure tensor itself does not move, but that is calculated in the frame of reference that moves with the fluid, are related by simple algebraic considerations. And I'll let you read those in the book, because it's not something that I feel we should spend too much time on. Okay. Let me just write the definition of the pressure tensor. We have seen this in our previous discussion of fluid equations. So this tensor here has a subscript 0, and this is what it looks like. And we have integral over the whole space of minus to plus infinity in each component of the velocity. Lowercase v is the particle velocity, u is the velocity of the fluid. And f is the distribution function, and I'm going to integrate over all velocities. Also, it may often be preferable to use scalar pressure. That's not a requirement, but that's what you're very often going to find in calculations. But for now, we'll leave the pressure tensor indicated as is. And if we use this definition by simple algebra, we rewrite the momentum equation as rho sub m mass density du dt plus u dot grad u. Maybe more familiar. Let me emphasize what this means. Equal to charge density times the electric field plus J cross B minus divergence of P naught. And of course, we're going to drop the subscript. The reason is that this is what we're always going to use. And it just needs to be understood what it is that we're using. And you can, if you have any doubts, let's see, let me square this equation. You can check the form of the equation. Does it look like the one on top of the page or the one that's squared? And looking at the momentum equation, if there is any ambiguity, it will tell you which definition of the pressure tensor you're using. Okay, so that was that for the momentum equation. You need a couple more things. An equation for, well, an equation relating the current to the electric field and the, the magnetic field, and a closure, which is called in our book an equation of state. I stick to my naming. That's a closure. It's not an equation of state, but you know what we mean. We've discussed this multiple times before. Let's try to get this wrapped up by today. The more, well, actually, both the Ohm's law and the closure could take some thinking and discussing. But the Ohm's law that you typically find is pretty simple form. If well, let's do it this way. J is going to be equal to sigma, where sigma is could be constant or could be a tensor, but let's keep it a little simple. And let me put primes here as our book does. But this is true in the rest frame of the plasma. And then what you do is do a coordinate transformation. If my plasma moves with velocity u with respect to the lab rest frame, then my J prime is going to be the same as J measured in the lab frame, but E prime is going to transform in a slightly more complicated way. That is, it's going to transform in E plus U cross B. Look here. Unprimed quantities are for the lab frame. Okay, and sigma doesn't change, stays sigma. Oops, what happened here? Therefore, the Ohm's law in the lab frame is going to look as J is equal to E plus U cross B. Now, if the plasma is sorry, collisionless, if there are no collisions, or the collision frequency goes to 0, then sigma goes to infinity, and therefore the quantity in the brackets must go to 0 at the same rate to have the product remain finite. Sigma goes to infinity, and therefore here E plus U cross B goes to 0. And that is the the Ohm's law that you'll often find in DLMHD, where the ideal comes from the fact that the conductivity goes to infinity, that means this inverse, which is the resistivity, goes to 0. Okay, this is apparently pretty simple, but in reality, it takes quite a bit of work to derive an Ohm's law from essentially from the momentum equations. And then one makes assumptions and simplifies the Ohm's law to the expression that we have above. I'm not even certain I want to write the whole thing, and definitely don't want to derive it. But the Ohm's law is quite a bit more complicated. The say the most notable terms are what's called the whole term that is proportional to J cross B, and the electron pressure term that is proportional to the divergence of the electron pressure tensor. Well, we got a couple of minutes left, or 5 or 10. So not long enough to really finish the discussion. And then let me just write this using again the notation in the book. E plus U cross B minus J over sigma. So that's the Ohm's law that's on top of the page. Is equal to, and here are all the other terms, and it's not 0, but 1 over E times N times J cross B minus 1 over E, and the denominator is the same, not accidentally, for all these extra terms. Divergence of PE, the electron pressure term, and then there is a term that special infusion plasmas never quite shows up. So that's dJ dt plus divergence of J U plus UJ. I should also mention that in general, there will be a term for involving the ion pressure as well. But that term is going to be smaller than the electropressure term by a ratio of the masses, and therefore it's never written. I've never seen it written. But depending on what you do, you may have to go that far. Okay, well, let me just type the names of these two terms. Maybe in quotation marks, their names. And this goes by variance of the pressure gradient, electron pressure gradient. Where here I don't, in fact, have a gradient, I have a divergence since we're using tensors. But if the electron pressure is scalar, that is, if that tensor is diagonal, then you end up with an electron pressure gradient. One thing that is worth noticing is that if I want to work with a single fluid, I get into trouble if I want to include these terms because, well, the electron pressure term depends on the pressure of the electrons, not on the pressure of the fluid. That means I need to keep the distinction between the two fluids. That is an indication of where a two-fluid model may be required. If my Ohm's law needs to include this term because it's comparable with the other terms on the left-hand side or not small enough compared to them, well, then a single fluid model is not sufficient for describing my plasma. And this is really all I wanted to point out about this part. Okay, next time we'll briefly chat about the closure, and then we can jump into doing some physics with MHD. Thank you for your attention, and we will see you next time.